basically they go into the other people's dream and then manipulate that people's mind, and then they change their behavior in the real world. Yeah, something like that, right? What happens if we mix the reality and dream? I mean, in the movie, I mean, it is not, I mean, the dream is, in the movie really feels like real life, right? So how we can distinguish movie and real life, and then yeah, in the movie, how we can distinguish between the movie and real life? How is that possible?
I'd like to go into your dream so that we don't have no more homework.
Oh, really? Actually, in my dream, I have a stack of homework, so I have a, yeah. Okay, that's an idea. So, in mind, okay. That's an idea. Okay. Good. Actually, I mentioned that movie because that movie is like derivative pricing. That movie is actually about derivative pricing, I think. Inception is a great movie about derivative and financial engineering. Let me explain why. In that movie, they basically go into people's dream and they do something and they can change the real life, right? And it is same. In derivative pricing, we also go into the dream, but not actually dream. We have to imagine, okay? We have to go into the imaginary world, which is called risk-neutral world, okay? It is not dream, but it is actually not real world. So it is kind of called risk-neutral world. And that risk-neutral world is strange. And in that risk-neutral world, everybody is risk-neutral. So in real life, everybody is risk-averse, right? But in that dream, or in that imaginary world, everyone is risk-neutral. If everyone is risk-neutral, then in finance, we learn that when we do the investment, we have to do risk-return analysis, right? But if we are in the risk-neutral world, in that situation, then what would be our analysis on asset? Do we really need risk-return analysis? Do we need risk? How do you think, Kevin? You excellently summarized the plot of the movie. So, if you are in an imaginary world where everyone is risk neutral, then how you can make financial decision? How will you do financial decision making? In the real world, we have to risk return analysis, right? But in that world, everyone is risk neutral. What we should do? Do we need risk-return analysis? Why?
Because there's no risk.
Right. No, actually there is risk, but no one cares the risk because we are risk-neutral. Risk-neutral means that if we suppose there is a gamble, if we draw coin, if we toss coin, if there is head, suppose we receive $200. If there is a tail, we receive nothing. Then expected value is $100, right? And if we compare that gamble and one certain $100 in this world, everyone favors $100 because expected value is the same, but there is a risk. Of course, we have there is a probability of $200, but there is also probability 0. So expected return is same, but there is a risk. So no one chooses that gamble. So everyone chooses $100 for sure. But if we are all risk neutral, basically they are identical to us because we don't care risk. So basically risk return analysis is unnecessary. We do only return analysis. There is risk, but we don't care risk. Okay, so if we care only risk, if we don't care risk and if we only care return, then what happens to supply demand of financial asset? What kind of asset do you want to buy? If you don't care the risk, you will only buy asset whose return is higher than others, right? And if some assets return is lower than the other, we will just short sell, keep selling it. then in the end, what would gonna happen in equilibrium? In equilibrium, if in that world, therefore people only care the return, and the people flock to the high return project and just show the low return project, then what would happen to the expected return of all projects? They should be exactly the same, right? Because again, in that imaginary world, everyone is risk neutral. They don't care risk, so now they care only return. Since they only care return, if a return is slightly high, everyone buy the return, and every return is slightly low, everyone wanna sell it. So return should be same for all assets. I mean, expected return should be same to all assets in the imaginary world. And if expected return is the same to all assets, then we know what that return should be. Can you guess? If expected return is the same to all assets, then what return it should be? What, Dave? Any idea? No, not zero. Okay. I mean, not zero because it should be equal to risk-free rate, treasury rate, basically. Because we don't care risk, and then there is already asset which doesn't include any risk, and it does always a fixed amount of money. That is risk-free asset. And at least we know the return of one asset, which is risk-free asset. Therefore, if no one cares the risk and everyone cares only about the return, and the return should be same to all assets, and that should be same to risk-free asset. Does it make sense? So let's go to Inception movie. So if we go to that dream or that imaginary world, which is called risk-neutral world, in a risk-neutral world, people don't care risk, and return should be same to all assets. So where we invest, it should generate exactly same excess return, which is zero, or gross return should be risk-free rate. Also, if we have a future cash flow in the risk-neutral world, then if we want to get the present value, we have to discount it at what rate? Risk-free rate, right? Because we don't care risk, so there is no risk-adjusted discount rate. So for every future cash flow, we can just discount it at risk-free rate, right? In corporate finance, when we discount the future cash flow, we use weighted average cost of capital. Weighted average cost of capital is weighted average between cost of debt and cost of equity. Cost of debt and cost of equity is basically risk-free rate plus risk premium. But since no one cares risk premium, there is no risk premium, zero. So therefore, discount rate should be risk-free rate. Does it make sense? Does it make sense? Any question until this is, I'm not joking, this is one of the most fundamental result in asset pricing. Okay, so you have to perfectly understand this concept. Any question until now? No? Okay. And then the surprising finding in derivative is that there is a slight difference between inception and then derivative pricing is that, okay, we go into the risk-neutral world and we calculate asset price, and what we know is that asset price is actually same to true asset price. That's the key difference between movie and then real life. In Inception, dream is dream. Real life is real life. We can manipulate somebody in the dream, we can change real life. People behave in real life. But in derivative pricing, it is similar but slightly different because if we calculate asset price in the imaginary world, that asset price is exactly the same to real asset price. It's surprising, isn't it? And that's how people got Nobel Prize, Black and Scholes. Black and Scholes got Nobel Prize because of that intuition. Okay, let me show you. Okay, so let's assume that we are in the risk-neutral world. Okay, risk-neutral world. Then, where is it? Okay. Okay, so risk-neutral world. So if we, so currently 6 months bond is something like this, and price is this one. So okay, interest up, go down. Let's call probability so the P. This is 1 minus P. Okay. Suppose we are in the risk-neutral world, then if we invest $1 in 6 months bond, then our return is gross return is this one. So this is 0.9% dollar, right? If we invest 1 year bond, then for the next 6 months return is 1.004 in upstate and 1.017%, $7 in down scenario, right? When interest rate is down. But if we are in the risk neutral world, our expected return should be exactly same whether we invest in 6 months bond or 1 year bond, right? It should be, right? In order to make them same, let's say the probability of this event is 1 minus p, or the probability of interest up is 1 minus p, or probability of interest going down is p. Okay? Then in the risk neutral world, we should have, okay, this one. In the risk neutral world, this one should be equal to, because this event is 1 minus p for right? Again, in the risk neutral, since return should be same to everything, every return should be same, it should be like this, right? It should be. Any objection about this one? No, it should be, right? And then actually this one is, if we rewrite this one is maybe 004 plus p one. It should be something like that. Therefore, we can solve for p, right? We can solve for p. So in the risk neutral world, there's p should be, therefore p should be, therefore this one minus this one divided by this one. So this one minus this one divided by this one minus this one. So probability is something like this, okay? Yeah, probability is something like this, okay? And then this, using this probability, actually you can now see that this probability is actually same to risk neutral pair going up. Oh, actually, I assume that this one is p. So sorry, this one is p, and this one is 1 minus p. Then I have to change. Sorry for the notation. So this is p, and this is 1 minus p. And then minus, something like this. So p is actually this one minus. So this probability should be, p should be looks like this one, and this is called risk neutral probability. So this is, should be the probability in that imaginary world in which the probability of interest rate goes up. The so in that imaginary world, in the risk neutral world, the probability that interest rate go up should be this one. Otherwise, this is not risk neutral world. Only in this probability, only in this probability, every asset return should be, every expected asset return is same. Okay, and then once we have this probability, now we can use this probability to calculate asset price for every asset. Okay, so let's calculate price of the long-term 1-year bond. Okay, price of the, in case of 1-year bond, interest rate go up is this one, going down is this one, right? So let's write down probability. So probability of going up is actually moving this one. So 1 minus P is 1 minus this one. Okay? So let's use that. Let's compute present value of the 1-year bond. If we calculate present value of 1-year bond, so it is probability going up. So this one occurs with this probability, this one occurs with this probability. So for 1-year bond, we can calculate expected value with some product such that this one multiplied by this one. Okay? This is a future value. Okay? This is future value of 1-year bond. And then we have to discount it back. Right? And then we have to discount it back with multiplied by exponential minus. And then the rate is, where is it? Where is it? Actually, let's use a discount factor. We can divide, we can multiply by, okay, let's divide this one by this one by 100. Okay? Actually, we have to multiply because we have to discount it back. Okay, discount it. Then you can see this number is exactly same to this number, right? That's exactly what I told. In imaginary world, we can calculate the once we get the probability, that should be the probability in risk neutral world. And if we apply the probability and calculate the expected value of 1-year bond and discount it back, and it becomes a real 1-year bond price. So remember, this is the bond price we calculated in the imaginary world, risk neutral world, and this is the real bond price, and they are exactly same. Right? So do you know what our idea? So now, since we know this idea, we can calculate derivative pricing very easily. Okay, we can do the derivative price very easily. So let's think about this bond put option. Okay, this bond put option. Again, in this bond put option's price should be, since this is the probability, and then what we can do is some product, this one, and then this probability, and then what? We can discount it back. It should be this price. Okay, so let's compare whether this is really that price. So derivative price, derivative. Let's use this derivative price. And then this derivative price is this one. Okay, you know, we calculate this derivative price with replicating portfolio, the pizza topping and pizza dough example, and this price is exactly same to this price, right? So again, this is very powerful thing. Okay, this is very powerful. We get, again, the idea is that we calculate the probability that should prevail in the risk neutral world, and we can simply use that probability in order to calculate the present value in that risk neutral world, and that price is exactly same to the true price. So this is a general rule. Actually, this is general result. When we calculate asset pricing, first, what you can do is, first you can assume that you are in the risk neutral world. Okay, you are in the risk neutral world, like Inception. You are in people's dream, but in that dream, everyone is risk neutral. And then in the risk neutral world, you use your common sense and get the risk neutral probability and asset return. And that asset return is actually real return. You can simply use that asset return or asset value that you calculate in that dream or risk neutral world, and you can actually use it in the real life because that is a correct one. Yes? Some product is like this one. Okay. Some product is, let's say it is 1, 2, 3, 4. Some product is, okay, this one multiplied by this one. Okay, and this is actually equal to this one multiplied by this one, and the sum. Okay, so some product, you do product and then sum. Product and sum. So suppose this occurs with probability 0.5 and this occurs with probability 0.5, then expected value is 1.5. Multiply this one, this one, this one, this one, and sum. Product each and sum. Okay? So this is sum product. I use some product to get the expected value, expected future value, and I discounted value. Actually, there is a nice interpretation about this future value, the expected value, about this sum product part. This is actually called forward price. This is exactly same to the forward price. So basically, forward price, what we are talking about in real forward price is actually expected value in the risk neutral world. And actually, this sounds strange, but I already proved it last class with this one. Okay. Where is this thing? Where is the PNG file? Okay. So do you remember this one? Okay. So actually, this is exactly what I use. So from the replicating portfolio, I showed how we can calculate derivative price, and that derivative price is exactly equal to this one. Calculate asset value with some probability that we calculated here, and we discount it with risk-free rate, and then this is called risk-neutral pricing. Okay, we put Q. Okay, Q is important because it distinguishes that we calculated expected value in risk-neutral world, not in real world. That's why I put Q over here. In the Inception, do you remember in the movie, because people get confused whether they are in dream or in real life, there are people use something, some device. What they use? Song. Song or what else? Song is one thing, and in case of Leonardo DiCaprio, the protagonist in the movie, what he used to tell whether he is in dream or not? Yeah, he used top, right? Something like this. And if it falls, he is in real life. If it keeps spinning, it is a dream. In derivative pricing, we have, and that is called totem in the movie. In derivative pricing, we have the same totem, which is actually Q. We put Q because we don't want to be confused that we are in real life on risk neutral world. So this is actually proof why it is identical to do the derivative pricing in real life, and assuming that in the real imaginary risk neutral world and calculate everything and become set. Okay. So anyway, if you take a look at the last line over here, actually this is actually clear because in this case we discounted it. We discount expected value in risk-free rate, right? It means already we are in risk neutral world because in real life we never discount some cash flow with risk-free rate. We have to discount with risk-adjusted rate, right? we discounted risk-free rate because we are in the risk-neutral world. And in risk-neutral valuation or in the risk-neutral world, when we do the valuation, basically, if we want to connect the real life in the risk-neutral world, what is going on here is that in real life, we get expected value objectively and discounted with risk-adjusted rate. But in the risk-neutral valuation, we always discounted risk-free rate, but instead we change the probability from real probability to probability that will prevail in the risk-neutral world. That's why I use the analogy that we are going into the risk-neutral world. Okay, is everything clear? This is a very fundamental result in asset pricing and very fundamental result in derivative pricing. Every derivative pricing is done this way, risk-neutral valuation. We go into the risk-neutral world and get the price and use that price in real life because we know they are the same. And this intuition is first discovered by Black and Scholes Merton. And that's why they got Nobel Prize. They didn't get Nobel Prize simply because they derived the Black-Scholes formula. That is actually high school math. It's very easy to derive a Black-Scholes formula. It is just high school math, and yes, it is high school math. Simply easier than high school math, actually. It's a simple calculus, simple integration. So they didn't get the Nobel Prize because that simple calculus. They got the Nobel Prize because they discovered this intuition of risk-neutral valuation. So this is very important. So from now on, therefore, what we can do is just simply we can calculate risk-neutral prices, risk-neutral probability, and use forever. Okay, use for every asset pricing, and that's all. So, for example, there is again this crazy derivative that pays where is B7. This crazy probability says that E pays the tangent expectation cosine sum of interest rate. In this case, it is again same. This is the true probability, and if we use risk-neutral valuation, again, this is sum product. So we got this one from the replicating portfolio, and then if we calculate this one in the using risk-neutral valuation, then we can do this one. First, this is forward price, and once you have forward price, then you can discount it back. This discount rate is this one. This time, let's use this one. Exponential of minus 1 year, 6 months rate is, where is 6 months rate? This one, and then multiply delta. And then they are again exactly same. Okay, and they should be same as I proved. Where I closed it. As I proved in the lecture note. Any question? So let's go to our original way. So let's download this one. So 그 학생들은 그 수업 시간에 그 수업하고 있는 거 알면서도 밖에서 떠들면 안 되겠지 이렇게. 예, 여러분은 절대로 이렇게 몰지각한 행동들을 하지 말기 바랍니다 정말. 내가 정말. 이건 대학생들이 너무 하는 거 아니야 솔직히. 수업하고 있는지 알면서 목도에서 왜들 떠드는 거야. 여러분들은 그러면 안 됩니다. 기본적으로 캠퍼스 내에서 공중도덕을 지켜야 될 거 아니야. 캠퍼스 내에서 막 걸어가면서 담배 피우고 막 그러대. 그래가지고 지난번에 아침에 기분 좋게 나는 대중교통수단을 이용하거든 주로. 대중교통수단을 이용하면서 이제 왕십리역에서부터 걸어오는데 아침에 상쾌한 기분에 걸어오는데 내 앞서가는 애가 담배 피우면서 걸어가니까 계속 걸어가면 담배 연기를 마셔야 되잖아. 막 따라잡아. 그래서 따라잡아서 앞질러 가면 되겠다고 앞질러 가시는데 걸으면 또 되게 빨라서 앞질러 가기가 힘들어. 진짜. 여기 담배 피우는 사람, 여기서 흡연하는 사람. 예? 길 가면서 흡연하지 마, 알았지? 뭐 안 하겠지만 예? 절대 걸어가면서 흡연하지 않기. 오케이? 아무튼 기본적인 것부터 합시다, 여러분. 자, anyway, let's use let's go back to our original example. In this case, let's delete everything. Now we don't need any. Don't worry, it is in the Google spreadsheet. So yeah, so it is fine. Okay. So because it is enough, as I told you, it is enough to calculate derivative pricing, right? And then we don't know bond price, and then so, okay. First, interest rate is like this, and then, okay, let me delete everything. Let's delete everything. Okay. So okay, so we came back to our original situation. So this is our data and interest rate model looked like that. And the bond price, 1 year bond price. So bond price, let's write down this one again. Bond price, maturity 0.5. It's simply, it is easy. Whatever happens, this is just 100. Yeah, whatever happens, it is just $100. 이상한데? 왜 갑자기? $100, and then bond price, 6 months bond price. We know this one, and this is actually this one. Okay, and 1 year bond price, it depends on interest. 6 months later, either it becomes this one or this one. Let's say probability of this one is P. Probability this one is P, and then given this probability should be consistent with this probability. Okay, therefore P is, let's say, our initial guess is 0.5, and then 1 minus P, let's say initial guess is 0.5. 0.5, then this is this one, and then this one, and then we discount it back with exponential of minus this one, and then okay, and we know this one and this one is different. Okay, this one and this one should be different. So pricing error is this one minus this one square. Oh. Okay, and we want to make this pricing error 0. Okay, other than they are consistent of each other, and then this one is, we can solve this one, data solve, and then target is this one, and I want to minimize this one by changing this probability, and this is this one. Oh, sorry, this should be 1 minus this one. Let me run this one again. Okay, so this is probability, and this is exactly what we obtained in the prior case, and this is exactly what make expected this probability, because this probability consistent with observed probability, and because we know this probability should be, because it doesn't matter whether we compute probability in risk neutral world or real world, it shouldn't matter. Therefore, this probability also should be consistent with risk neutral probability that we computed as in the previous case, right? So this should be the risk neutral probability, because the real probability is consistent with the risk neutral probability. Again, to remind your memory, because this should be the risk neutral probability, because prices are consistent. Prices are consistent, right? In risk neutral world or real world. So to remind your memory, okay, this is the risk neutral probability. This should be, if we calculate 6 months, the risk neutral world is this one multiplied by delta, and the up probability, so it is our risk-free rate. Move this one, risk-free rate, and then this is up return is this one divided by this one, and then down return is this one divided by this one. So this risk neutral probability is therefore this one minus this one divided by this one minus this one. So they are exactly same. Okay, they should be same because again, if we use this probability, this should give exactly the same bond price that observed one, and the probability then make the observed price exactly same to the expected discount future value, because they are identical. So these two probabilities should be same, and indeed they are same. Yes. Yes. So this is the one. So what we can do is, in this case, we use long-term bond price, 1-year bond price, and we find the probability that makes probability that is consistent with observed probability, and that should be same to risk neutral probability. And by the principle of risk neutral valuation, we use that probability for every derivative. So for example, suppose we have a derivative. So derivatives, it pays like $10 and minus $5 here. Then this derivative price should be same to some product, this one, and then this one. This is the full price of the derivative, and then we discount it with and this is the derivative price. This should be the derivative price, and you can, in your home, you can prove that this is indeed the derivative price by constructing replicating portfolio. I taught you how to construct replicating portfolio, and the value of the replicating portfolio should be exactly the same to this one. Okay, so do you get the general idea of how we can do the derivative pricing? Okay, from bond price, we extract risk neutral probability, and once we have risk neutral probability, it is done. Risk neutral probability, everything. Once we have risk neutral probability, we can calculate just expected value and discount it with risk-free rate. Done. So simple, isn't it? So this is the beauty of risk neutral pricing. I think the time's up. So this Friday, let's investigate slightly more complicated one. Let's investigate slightly more complicated tree structure this Friday. Okay, see you this Friday.